So my name is Scientific Sally, and I am a mad scientist. I am not a mad scientist like, I don't like little kids and I don't like anybody. I just want to stay in my room all day long. No, I am a mad scientist because I am mad about science. I love science. And what I'm going to do today is I'm going to show you a couple of really, really fun things having to do with Earth, having to do with rocks, having to do with energy. I'm just going to try to stuff as much science at you as I possibly can today. So we're going to go ahead and get started. Now I'm going to start you off with something very, very easy. When we have the Earth in front of us and we were to take a huge knife or do a huge karate chop in the middle of the Earth and open it open, how many layers would we see? That's right. We would see 3. If some of you said 4 because you count the core as inner core and outer core, you're right as well. So what we have right here is I'm going to show you a very, very quick picture of the Earth chopped. And as you can see here are all the different layers that they have. So we're going to go over them very, very quickly. And if you want, either now or later, you can participate and do your own family Earth at home. So what I want you guys to do is I want one person to stand up straight as possible, and you represent the crust. The crust covers the Earth. It is the outermost layer, and it is it's thin and it is solid. All right, so just stand just like that. Another family member can come up, or another friend can come up, and they can kneel right in front of you. And I want you guys to wave your arms as you're kneeling. And what you have here, you're representing the mantle. The mantle is thicker than the crust, a lot thicker than the crust, and it's mostly made of one specific type of liquid rock, okay? And it is right in the middle, so just keep doing this. And then the last layer is the innermost layer, and it is the core. And you can have one family member get on their bottom and tuck themselves into a ball, and they're going to represent the core. It is the heaviest. It is why it gets pulled towards the center. And those are the layers of the Earth. Did you guys do it? Were you guys able to do it? All right, if you want to do it later, okay? So now that we have that, you can also imagine a hard-boiled egg. If you imagine a hard-boiled egg, when you look at it and you cut it in half, you have 3 layers. You have the shell, you have the white of the egg, which is like the mantle, and then you have the yolk, which is the core. Well, before you chop it open and you are about to enjoy your yummy, yummy, hard-boiled Earth egg, you need to do what? That's right, you need to crack it. Well, when you crack it, what I want you to imagine, since now we're using this as a good analogy for the Earth, is I want you to imagine that those cracks are tectonic plates. The Earth, when you break them up, the Earth has these tectonic plates, and the Earth and the waters all rest on top of these tectonic plates. And they're all over the Earth. I'm going to show you a quick picture. See? They're all over the Earth. A little bit better. There you go. All of these represent tectonic plates. And these plates, they move, they rub up against each other, and sometimes they go over each other or under each other, and they produce pretty awesome things. Sometimes not so awesome things. Sometimes they produce folds and faults, okay? So we're going to talk a little bit about these folds and faults. And you can see right here, I have an example of the Earth, the crust. And right here, I have these moves. And these moves, for example, if I strike slide, this is called a strike slip, and it's just whenever they move, these tectonic plates move, and they move from side to side. And they can produce valleys, trenches, all sorts of things. And then you also have the normal type, which is whenever they shift up. And this is where you might get like a mountain, a hill, anything like that. And then you have something that's called the reverse, which is instead of it going this way, which is the normal, it goes like this. And then you get something that's more of a valley or like a canyon, okay? So those are the faults that you can see. You can also see folds in the Earth, which I'm going to represent by using these foldable, pliable sponge pieces right here. And you can do all sorts of folds. You can do an anticline, which is more of a smaller version of a mountain, like a little hill or something like that. You can do a syncline, which is something that looks a little bit like this. And then you have a monocline, which is something that kind of starts and it almost looks like a slide as it goes down. So all these faults and all these folds that happen when these tectonic plates move, they do something. They cause not only formations in the earth, but they release something. Can anybody think of what they release? If you guys said energy, you're 100% correct. They release energy. They release it whenever they move, and whenever tectonic plates move like this or these rock formations, what happens is that not until that rock stabilizes will the energy stop being released. So depending on how big that shift was, depends on how big that energy is. Well, now that I brought up the word energy, let's think about that. Energy. What is energy? The simplest way to be able to describe to you what energy is name something you did this morning. I brushed my teeth. I had breakfast. Maybe you went outside and took a walk. Maybe you just simply got out of bed and put on some clothes. Anything like that, all those things require energy. And you can't just make energy. And that's called, what happens is the conservation of energy, where energy can only get transferred. It cannot get created. It can't be destroyed. It can just be transferred from one thing to another. So the most popular type of energy that kids usually hear is kinetic and potential. And the easiest way for me to show you an example of kinetic and potential is by either using a rubber band or a ball or both. Here I have a ball, and this ball right here has potential energy. It's not moving, but potential energy means that it's stored and it has the potential to do something. So this is potential energy. When I decide to put a force to it, and it's moving, it is now kinetic energy. It is energy in motion. And as it's traveling up, it is also kinetic energy. When it tops right here, it's potential for just a split second, and then as it comes back down, it's kinetic again. And once it rests on my hand one more time, it's potential. You guys can do your own version of potential and kinetic energy by playing the red light, green light game. You guys ever done that? Red light, green light's pretty awesome. You go back here, and you guys all start in a line, social distancing if you want. And what you do is, instead of saying red light, green light, you say potential, kinetic. And every single time a person says kinetic, you move. When they say potential, you store your energy, and you stay still. And you go kinetic, go, 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 go. You move, energy in motion. When they say potential, you stop, all right? So that's a cool game that you guys can play at home. So here I have my rubber band. And my rubber band is a great example of kinetic and potential energy, because you know that rubber bands have a ton of potential. They're by themselves right here, and whenever they stretch, and then you release it, all that energy is released. And depending on how much you stretch, depends on how much energy you're allowing it to go, how much energy you're allowing it to go from one place to the other. Here, I have a catapult, and my catapult is forced by rubber band energy, okay? Rubber energy. And when I push down, I'm stretching these rubber bands. And when I put this right here, what do you think is gonna happen when I push this button? Let's do a countdown. 3, 2, 1. Bombs away. There they go. So that is a great example of energy that we see every day, kinetic and potential. But there are other types of energies that we see every day. For example, we have this right here. This is called a radiometer. And a radiometer is a great explanation of how we can use light energy, the heat of the sun or any other source of light that you might have. So here, I'm going to place this right down here. I'm going to push my video down a bit so that you guys can see it a little bit closer. There we go. And once I get everything to stop moving, you'll notice that the diamonds on there are two colors, black and white. And there is a reason why they're like that, because the black squares absorb the light and the white ones reflect the light. And then whenever I put a flashlight next to it, it causes it to spin. And that is how we can use light energy. And as you can see, it's spinning faster and faster. And that is how we can use light energy to be able to work for us. Another way that we can use light energy, boy, that's going fast. Another way we can use light energy is with solar panels. You guys have probably heard of solar panels before. And these solar panels, right here, these solar panels look kind of like that. This is a very small solar panel, but there are solar panels that you see on houses, even on stop signs, or on anybody's yard. They have the little light up stakes, and they have solar panels. And what these do is they absorb the light from the sun, and it allows them to be able to power themselves at night. So here you have a solar panel, and we're going to see what the solar panel is supposed to do. Makes my little buddy here work. The energy that the light is shining on that solar panel allows this to work with absolutely no batteries. So let's see it walk for a little bit. Move my panel, my faults over here. All right, let's see it. Oh, now it's getting shy. Let's try again. Looks like I might only want to do it while it's up here. It's spoiled. All right. Okay, so that's different type of energy. So there's light energy, there's kinetic energy, potential energy. There's also energy that we can use, like I said, to work for us. Solar energy is one of them. Another one is wind energy. Wind energy has been able to help us as well. And as you can see here, I have a windmill. You guys may have seen something like this before. And what you need to focus on is this light right here. It's a diode, and it should light up red when this starts working. Okay, so let's see. Does it work? Yeah, it works. Okay, so whenever I take this outside and it's a nice windy day, this will keep spinning, and as it keeps spinning, this light will automatically work. We use that to our advantage to be able to convert the wind, the energy of the wind that's making this spin, to do work for something that we have to do, such as even power electricity. I have a quick poster to show you, so that you can see all the different types of energy sources that we have. We have energy, we have renewable energy, which you can see in geothermal, hydroelectric, solar, and wind. Wind, which we just talked about, and solar, which we just talked about. And then you have non-renewable energy, such as coal, gas, nuclear, and biomass. And here I have a map, if you're able to see it a little better, but this map will be able to show you some places where you can naturally see the solar energy working, the hydroelectric energy working, the nuclear, the gas, and all sorts of things that we come across every day. So there you can see some examples of that. Okay, so now that we have talked about energy, and now that we have understood, hopefully, we understand a little bit more about energy and how we can find it, now we can talk a little bit more about going back to when those tectonic plates move, they release energy. And sometimes faults and lines, they get moved and they create formations like mountains, trenches, valleys, but sometimes they create earthquakes. They create these seismic waves that release a ton of energy. And these waves, you can see them in a seismograph, and I have an example of a seismograph right here. And as you can see, I'm going to try to put it next to my lab coat so you can see a little better. but it kind of looks like a machine that measures like your heartbeat. But what this does is this measures all sorts of things that a seismologist uses to be able to know when the earthquake happened, how strong it was, where the epicenter is going to be located. This helps them out a lot, and it allows them to be able to see it as it's happening, before it's even happening, and afterward try to learn from it. So in California, there's a fault line there, the Andreas Fault, and California is very, Californians are no strangers to earthquakes, and they have to do things a little bit differently, just like we do things a little bit differently because we prepare ourselves for hurricane season because we're no strangers to hurricanes. They have to prepare themselves, and they have to prepare their buildings, and they have to try to make them as earthquake resistant as possible. So here I have 2 earthquake buildings. They are built differently. This one is all built the same. They're all in same line. I made sure that they were all single file line down straight in a row. And then I have this one, which is more like the Jenga setting, where I have these facing one way and these facing the other way, and so on and so forth. So I'm going to give you guys a couple of seconds to decide which one do you think is going to be the more earthquake resistant. This one, where it has all of the small blocks facing the same way, or this one where it has all of the blocks facing differently. All right, let's find out. What I'm going to do is I'm going to bang the table, and we're going to see which one is affected the most. 1, 2, 3. We got our answer, didn't we? Yes, this one is a lot better. And the reason for that is because as I am banging the table, what happens is once one of these layers start to move, all of the layers start to move in the same direction. However, here, because I have one of them facing one way and the other one facing the other way, whenever I move it, it doesn't cause, there's minor shifts. When this one moves the other way, and it almost counterbalances. Now, volcanoes, which is what I have right over here, volcanoes also tend to, the tectonic plates, they sit on top of the lava. And whenever you have a non-explosion, lava creeps out of there, and it creeps out at a very slow and steady pace. But when you have an explosion, something completely different happens. When you have this, you have, like I said, the plates sit right on top of the magma. And the magma, after a while, the pressure is going to build. And as these tectonic plates start moving and the pressure is building, the magma finds its way in between the tectonic plates, and it goes straight up and it causes an explosion. So what I'm going to do is I'm going to do a volcanic explosion to show you how that happens. I'm going to do it with the classic acid-base reaction. I'm sure you guys have already seen it before. It's where you have vinegar, and it's where you have baking soda. And for those that are experts, you know that you need to add soap to it. And the reason for that is because even though the lava is coming out of the volcano fast, it's also not moving super, super fast. So the great thing is that the soap will help dial it down a bit. Now, let's see if I have the time. I do have the time. So what I'm going to do is, before I show you this, I'm going to show you a way that mad scientists are able to freeze an explosion. And we do it by using slime. So here I have your base, which is baking soda. And we use PVA to make our slime, which is the same thing that you would use if you wanted to use glue. So I'm going to put some PVA right in there. Okay. And I'm going to stir it up just a little bit. Use a marker right here. All right, just to get everything spread out. And I'm going to go ahead and make it a color just so you can see it a little bit better. Now the next thing I'm going to do is I'm going to put something called sodium borate. It's a solution that we make. You guys might use borax, which is fine. But with the sodium borate that we use, we add acetic acid, which is vinegar. So now you have your volcano explosion. You already have your ingredients there. You have your acid and you have your base. But when you mix it in with ingredients for slime, like I said, you get something a little bit different. Are you ready? 1, 2, 3. See? You get a magic muffin. So what happens is you have slime and a volcanic explosion mixed into one. You can see it's hard. And what happens is the reaction basically got suspended. The acid-base reaction basically got suspended in slime, which is why you see a little jiggly muffin right on top of there. So if I take, I'm going to get a trash can, guys. If I take this and get all the liquid out, I'm going to scoop it out. Whoa. And I'm going to squeeze. And I'll squeeze some more. Squeeze some more. At the end, you just get left with mostly the PVA, which is just a fancy word for saying a plastic. Okay, and we see polymers like that all the time in plastic bags, our skin, gum, rubber bands. So out of all of that explosion, you end up with this. Pretty cool, huh? All right, are you guys ready for the explosion? All right, let's do this. So what we're gonna do is we're going to take all my stuff and put it right over here. All right. Okay, and right here I have my volcano. If you guys don't mind, I'm gonna move you in a little bit closer. Don't mind the big noise of these table mates. There we go. All right, so then what we're gonna do is we're going to, I have behind this volcano, I have a flask. And the flask has, that's right, baking soda. So to this baking soda, I'm going to add some yellow food coloring. I'm just gonna squeeze it in there. All right, and I'm gonna mix it up. And then what I'm gonna do is I'm gonna take soap. Soap is a very important ingredient. And I'm gonna put some right in there. Again, the more soap you add, the more it's gonna allow the lava coming out to be slower and thicker and just come out really slow. So there's my mixture right in there, okay? So then the last thing I'm gonna add is going to be my vinegar, okay? And the vinegar is colored red. So are you guys ready for the explosion? All right. 5, 4, 3, 2, 1, and go. Ooh. You guys see how that's coming out? And it's coming out thick and bubbly. And it's going to take a while for it to keep coming out. And you can see that it's coming all the way down. I got my streaks of yellow. My combination made it orange. This is your classic acid-base reaction. And in doing it, it did require energy. Not the kind of energy that a real volcano uses to be able to get that huge explosion. But it did create energy, and it did create, I mean, not create energy, but it did need energy in order to happen, in order for it to go up. And the only reason it was able to go up is because we created something called carbon dioxide, okay? And those are all the bubbles that are in there. All right, guys. I hope you had a really good time. I always have fun whenever I share science. If you have any questions, please feel free to put them down in the comments and I'll be more than happy to answer them. Thank you so much. I had a whole bunch of fun and I hope you guys had a bunch of fun. Thank you to the Houston Gem and Mineral Show for inviting me. I had a great time.